Hello friends, welcome to my channel. Let's have a look at problem 766, Toeplitz Matrix. In this video, we're going to share two solution formats for this daily challenge problem. The first one is based on compare the nearest lower right neighbor. So in other words, this is the mathematical definition. The second one, actually marked by treatment 1, is going to be based on check linear equations. So first, I'll give some background. So in linear algebra, so a Toeplitz matrix or diagonal constant matrix, so named after Otto Toeplitz, is a matrix in which each descending diagonal from left to right is constant. For example, this is an example of Toeplitz matrix. So here you can check A and B. So here is should be B. So if you check the diagonals, this is C, this is D, this is E. So first I'm going to give a solution based on the treatment 2. So for each position RC, so there should hold the matrix RC equals the matrix R plus 1, C plus 1 for Toeplitz matrix. So this is actually the definition of Toeplitz matrix in terms of generic element. So we'll first present this format, and then we want to do another format by checking diagonals from top left to bottom right with mathematical equations. So first, let's look at the simpler one, or the neat one. So this is based on the definition of based on generic element. So first, I'm going to track the number of rows and number of columns of the given matrix. Let's call them M and N. So this way, actually, we get the number of rows, number of columns. This is not absolutely necessary, right? So, but we want to make it more organized, and then we just need to iterate, right? For R in range. So here I'm writing M minus 1. The reason is that I want to check R plus 1. We want to make sure R plus 1 is inbound. Similarly for C in range N minus 1. So we want to make a column also inbound. Then we're going to check if matrix RC it does not equal to matrix R plus 1, C plus 1. In this case, we can make sure that this matrix is not a Toeplitz matrix. So we're going to return false. So if after the for loop nothing returned, so we're going to return true. So this is the one format of solution, so which is a neat one based on the generic elements. So let's do a check. Yeah, it passes the first example. Now let's look at the generic case. Yeah, it passes all the test cases. So now let's look at the second format based on treatment 1. So basically we want to write the linear equations for each of the available diagonals, and then we check if in that diagonal or in that line, so there is only one constant element, right? So this way, let me copy the function signature, and let's change this function signature to be v1, and then let's do the similar thing. So let's get M and N first. So for M by N matrix, there will be N minus M. So how many diagonals? So there's, for example, here is 3 times 5. So here 1, 2, 3, 4, 5, 6, 7, 8. Right? M plus N minus 1. Right? So the equations is given by R minus C equals from the bottom corner. So that is M minus 1. Then M minus 2. So this one is 0. Then this will be 1, negative 1. This will be negative n minus 1. So with that said, let's do this. So we are going to do it in a brute force way to understand the details. So for difference, so this difference means r minus c, or you can understand as x minus y by putting it in the coordinate system. But notice that the x-axis is downwards, right? So for in range, so m minus 1, so I'm going to write negative n, right? Yeah, negative 1. So the reason is that it ends at negative n plus 1. So with that said, we can initialize a temporary variable called set, right? And then we want to find all the elements in the diagonal, and then to check if this diagonal contains only one unique element. Then this is simple. For r in range m, for c in range n, right? So we're going to check if r minus c equals the diff. So if this is the case, it corresponds that this in the diagonal r minus c equals diff, right? So then we're going to add this matrix element to the set, right? So it's rc. And then afterwards, so we're going to check if this length of this temp is greater than 1. If so, we're going to return false. It means that in this diagonal there are more than one unique elements. So if after the for loops nothing has returned, so we're going to return true. So this actually is the second format we want to present. So this is more verbose and more complex than the first version, but it's good to know. So let's do a check. Yeah, it passes one example. Now let's look at the generic case. Yeah, it passes all the cases. So I guess here we can do the second version as due to the problem size on the constraint. For example, the m and n is bounded above by 20. So it's a very small size, right? Even if you do a triple loop, it's 20 to the power 3, right? Something like that. That will be the problem upsize. So with that said, I guess that's about it for this easy problem and for this video. Thank you.